You know that feeling when you open your fridge expecting to find leftover pizza, but instead there's a pineapple pizza that you definitely didn't order, and now you're questioning everything you thought you knew about your roommate? Yeah, that's basically what happened to astronomers on August 24th, 2025. They pointed the Keck telescope at 3I/Atlas expecting to see, comet stuff. Water, dust, maybe some carbon dioxide. Normal comet ingredients. Instead, nickel vapor and cyanide in a pattern that makes absolutely zero sense. And the more they studied it, the weirder it got. It's like the universe looked at our textbooks and said, "Cute theories you got there. Would be a shame if someone completely invalidated them." Welcome back to the channel, folks. If this is your first time here, hit that subscribe button because we're about to dive into one of the most bizarre discoveries of 2025. And if you've been following the 3I/Atlas saga with us, buckle up because this one's a game changer. So let's talk about what happened. 3I/Atlas, our friendly neighborhood interstellar visitor, number 3 on the objects from another star system leaderboard, was cruising through space, minding its own business. It's about 257 million miles from the sun right now. That's roughly the distance you'd travel if you drove your car for about 400 years nonstop. Don't try that, by the way. Your gas mileage would be terrible. Now, astronomers at the W.M. Keck Observatory in Hawaii, bless their souls, decided to use this crazy instrument called KCWI. That stands for Keck Cosmic Web Imager, which sounds like a Marvel superhero gadget, but is actually even cooler. It's an integral field spectrograph. And I know what you're thinking. Wow, that's a lot of fancy words strung together. Let me break it down. Imagine you're at a rock concert, but instead of just hearing the music, you have a device that tells you exactly which instrument is playing, where each musician is standing on stage, and what note they're hitting at any given moment. That's basically what KCWI does, except instead of music, it's measuring light from different gases around the comet. And instead of instruments, we're mapping chemical elements floating in space. Pretty cool, right? So they pointed this thing at 3I/Atlas and captured about 15 minutes of data. Just 15 minutes. That's less time than it takes to watch an episode of The Office. But in those 15 minutes, they captured something that's now making scientists rethink everything we thought we knew about comets from other star systems. They found two gases. First up, cyanide. Now, before you panic, cyanide in comets is actually super common. It's everywhere. It's made of carbon and nitrogen stuck together, and when sunlight hits it, it glows. Scientists love detecting cyanide because it tells us about the chemistry inside the comet. It's like a chemical signature saying, "Hey, I'm made of this stuff." But here's the kicker. They also detected atomic nickel vapor. And when I say atomic nickel vapor, I mean individual nickel atoms just floating around in space, like tiny metallic ghosts. And this is where things get bonkers. Nickel emission from comets isn't completely unheard of. We've seen it in a few comets from our solar system, and we saw it in 2I/Borisov, the second interstellar visitor. But this is the first time anyone has mapped out exactly where the nickel is compared to where the cyanide is. And folks, they are not in the same place. Nickel stays super close to the comet's nucleus. We're talking about 594 kilometers. That's like the distance from New York City to Cleveland. Tight, compact, hugging the nucleus like it's afraid to leave home. Cyanide? Cyanide is out there living its best life, spreading out to 841 kilometers. That's like going from New York to Charlotte, North Carolina. It's traveling, it's exploring, it's seeing the world. Now you might be thinking, okay, so what? Different gases spread out differently. Big deal. But here's why it's a big deal. If both gases were being released the same way, if they were just evaporating off the surface of the comet like ice cubes melting on a hot day, they should spread out at roughly similar rates. Solar radiation hits them both. The physics should be the same, but it's not. Nickel stays tight. Cyanide spreads wide, which means the nickel isn't coming from the surface. It's coming from something else, something that breaks apart really fast. So, where's the nickel coming from? Scientists have two main theories, and both of them sound like rejected band names. Theory number one, metal carbonyls. These are molecules where a nickel atom is bonded to carbon monoxide molecules. The most famous one is nickel tetracarbonyl, which has the chemical formula NiCO4. Say that 5 times fast at a party, and people will think you're either a genius or having a stroke. These molecules are super fragile. Like, sneeze too hard and they fall apart fragile. When UV light from the sun hits them, boom, they disintegrate instantly, releasing atomic nickel vapor. That's why the nickel stays so close to the nucleus. It doesn't have time to spread out. It's like when you open a bag of chips and they immediately go stale because you live in a humid climate. Happens too fast. Theory number two, metal attached polycyclic aromatic hydrocarbons, or as scientists call them, metal PAHs, because even they got tired of saying the full name. PAHs are these complex organic molecules made of carbon rings fused together. Think of them like molecular Lego structures. And apparently, nickel can hitch a ride on these PAH molecules. When sunlight zaps them, the nickel gets knocked loose. Either way, the point is this: nickel isn't sublimating directly from ice. It's locked inside these fragile parent molecules that explode under solar radiation. That's why it stays concentrated near the core. Now, here's where things go from interesting to wait, what? In our solar system, every time we detect nickel vapor in a comet, we also detect iron vapor. Always. Without fail. Iron and nickel are like peanut butter and jelly. They form together in dying stars, get scattered by supernovae, mix into interstellar dust together. Where you find one, you find the other. But 3I slash Atlas? Nickel, yes. Iron? Nope. Nada. Zilch. Zero. Not even a trace. And here's the plot twist: 2I slash Borisov, the previous interstellar comet, had the same weird signature: nickel, but no iron. So, what does that tell us? Either these interstellar comets are pulling some kind of magic trick where they hide their iron, or, and this is the mind blowing part, they formed in star systems with completely different chemistry than ours. Think about it. Every comet in our solar system formed from the same protoplanetary disk 4.6 billion years ago. Same ingredients, same recipe, same chef. But 3I slash Atlas? It formed around a different star in a different part of the galaxy, possibly billions of years ago. That star might have had different metallicity, different element ratios, a completely different chemical environment. It's like if you grew up eating Italian food your whole life, and then someone hands you authentic Korean barbecue. Same concept, food, but completely different flavor profile. That's what's happening here. Same concept, comet, but wildly different chemistry. And this is forcing astronomers to confront an uncomfortable truth. We've been assuming all comets are basically the same because the only ones we've studied are from our solar system. But now we're getting visitors from other neighborhoods, and it turns out the universe is way more diverse than our backyard suggested. 3I slash Atlas is basically a cosmic delivery package from another star system. And when scientists open that package and analyze what's inside, they're learning that the chemistry out there can be fundamentally different from what we have here. Every star is unique. Every protoplanetary disk has its own fingerprint, and every comet carries that signature with it. Based on 3I slash Atlas's trajectory, we know it's coming from the thick disk of the Milky Way, a population of older stars. In the last 10 million years, it's passed within about 3 light years of 25 known stars. But which one, if any, was its parent? That's still a mystery. What we do know is this: wherever 3I slash Atlas came from, the conditions were different enough to produce a comet that doesn't match anything in our solar system. And that's huge. That means the models we've been using, the assumptions we've been making, they're incomplete. Now, let me tell you where 3I slash Atlas is right now, because the timing here is kind of hilarious in a frustrating way. As I'm recording this on October 16th, 2025, guess where the comet is? Behind the sun. From Earth's perspective, the sun is directly between us and 3I slash Atlas. We can't see it. Ground-based telescopes are blind. It's like trying to take a selfie with the sun in your eyes. Not happening. But here's the good news. Around late October, early November, 3I slash Atlas will emerge from behind the sun and we'll be able to observe it again. By then, it'll have passed perihelion, its closest approach to the sun, which happens between October 29th and 31st. That's the critical moment. The intense solar heat could fragment the comet, ignite new outbursts, change its chemistry completely. Scientists are basically on the edge of their seats waiting to see what happens. And when it reappears, you better believe every telescope on Earth and a few in space are going to be pointed at it. We're talking about post perihelion observations that could reveal entirely new behavior. Did the nickel emission change? Did iron finally show up? Did something else activate? We're about to find out. But let's zoom out for a second and talk about the bigger picture here. 3I Atlas is only the third interstellar object ever detected. 3. That's not a lot. You can't build a comprehensive scientific model with 3 data points. It's like trying to predict the weather for an entire year based on 3 random days. Not ideal. But here's the exciting part. That's about to change. The Vera Rubin Observatory is coming online soon, and it's going to scan the entire sky every few nights. Scientists estimate it'll discover dozens, maybe hundreds of interstellar objects in the next decade. And every single one will be a new chemical fingerprint, a new puzzle piece, a new window into how different star systems form comets. Imagine having a catalog of comets from across the galaxy, each one tagged with its chemistry, its origin, its story. That's the future we're building toward. And 3I Atlas, with its nickel and cyanide weirdness, is paving the way. So, what did we learn today? 3I Atlas is spitting out nickel vapor that stays weirdly close to the nucleus and cyanide gas that spreads way farther. Iron, which should be there, is mysteriously missing. This chemical signature doesn't match any comet from our solar system, proving that comets from other star systems can be fundamentally different. The textbooks we've been using, they're based on studying comets from one star system, ours. But now we're getting visitors from other systems, and it turns out the universe has a lot more variety than we thought. That's not a failure of science. That's science working. We observe, we test, we find anomalies, we revise our models, we get better. And folks, this is just the beginning. As more interstellar visitors show up, we're going to keep learning, keep revising, keep expanding our understanding of how the cosmos works. And honestly, that's the coolest part of astronomy. The universe keeps surprising us. But astronomers at the WM Observatory had a plan. They were using an instrument called KCWI, the Keck Cosmic Web Imager. This isn't your average telescope camera. KCWI is an integral field spectrograph, which means it doesn't just take a single picture of the comet. It captures the spectrum of light from thousands of points simultaneously, creating a three-dimensional map of which gases appear where around the nucleus. Think of it like using a heat sensing camera to see which parts of a campfire are hottest, except here, they're mapping which chemical elements appear at different distances from the comet's core. And what they found was remarkable. 2 gases were being expelled from 3I Atlas. First, cyanide or CN, a compound made of carbon and nitrogen bonded together. Cyanide in comets isn't rare. It's actually one of the most common molecules we detect. When sunlight hits cyanide molecules, they fluoresce, emitting light at specific wavelengths that tell us about the carbon and nitrogen chemistry inside the comet. Second, atomic nickel vapor. And this is where things get interesting. Nickel emission from comets isn't entirely new. It's been detected in a handful of solar system comets, and it was seen in 2I Borisov, the second interstellar visitor. But this is the first time scientists have created a detailed spatial profile showing exactly where nickel and cyanide are located relative to the nucleus. Here's what the data showed. Nickel has an e-folding radius of 594 kilometers. That means most of the nickel emission is concentrated within about 600 kilometers of the core. Cyanide, by contrast, spreads out to 841 kilometers, about 40% farther from the nucleus. Why does this matter? Because if both gases were being released the same way, if they were both just sublimating directly from ice in the nucleus, you'd expect them to spread out similarly. Solar radiation pressure affects all molecules. The expansion dynamics should be comparable. But that's not what's happening. Nickel stays close. Cyanide spreads wide. This spatial difference is the key to unlocking what's actually happening chemically inside 3I/Atlas. And it's forcing astronomers to rethink how metal vapor escapes from comets. In our solar system, comets are basically dirty snowballs. They're mixtures of ice, dust, and rock left over from the formation of the planets 4.6 billion years ago. When a comet gets close to the sun, the ice sublimates, turning directly from solid to gas without passing through a liquid phase. That outgassing carries dust particles along with it, creating the beautiful tails and glowing comas we see in the night sky. Most of that gas is simple volatile molecules: water vapor, carbon monoxide, carbon dioxide, methane, ammonia. Things that sublimate easily. Metals like iron and nickel, on the other hand, are usually locked in dust grains, tiny solid particles that don't vaporize until the comet gets extremely close to the sun, maybe closer than Mercury. But 3I/Atlas is different. It's releasing atomic nickel vapor, not dust, not molecules, individual nickel atoms floating freely in space. And the pattern of that release doesn't match what we see with other gases. So, where is this nickel coming from? The team behind the Keck observations proposes two main theories. Theory 1: metal carbonyls. These are compounds where a metal atom like nickel is bonded to carbon monoxide molecules. Nickel tetracarbonyl, chemical formula NiCO4, is a classic example. These molecules are extremely fragile. When UV light from the sun hits them, they break apart almost instantly, releasing atomic nickel vapor. Theory 2: polycyclic aromatic hydrocarbons with attached metals, or metal PAHs. PAHs are complex organic molecules made of fused carbon rings. Think of them like tiny molecular benzene rings stuck together. Some researchers think metals like nickel can attach to these PAHs, forming compounds that survive in the cold of interstellar space. When these molecules are exposed to sunlight, the nickel atom gets knocked loose, creating the vapor we detect. Either way, the key point is this: the nickel isn't coming directly from the nucleus. It's being released from parent molecules that dissociate very quickly after being exposed to solar radiation. That's why it stays concentrated near the core. It doesn't have time to spread out before we detect it. Now here's where things get really interesting: the missing iron mystery. In our solar system, when you detect nickel vapor in a comet, you almost always detect iron vapor too. In fact, iron is usually more abundant than nickel. That's because both metals form together in similar cosmic processes. They're forged in the cores of dying stars, scattered by supernovae, and mixed into interstellar dust in tandem. Where one is found, the other is almost always present. But 3I/Atlas? Nickel, yes. Iron? Not detected. And here's the kicker: 2I/Borisov, the previous interstellar comet, showed the same pattern: nickel vapor, but no iron. This isn't a coincidence. This is telling us something fundamental about how comets form in other star systems versus ours. One possibility is that the parent star of 3I/Atlas had a different chemical composition than our sun, different metallicity, different element ratios. So the protoplanetary disk where 3I/Atlas formed had more nickel relative to iron. Another possibility is that the processes that concentrate metals in cometary materials, things like ice sublimation, photochemistry, radiation exposure, might work differently in other stellar environments. Whatever the answer, it's forcing astronomers to rethink their models. The textbook assumption that all comets form similarly just doesn't hold up anymore. Every star is unique. Every protoplanetary disk has its own chemical fingerprint. And every comet that forms carries that signature with it. 3I/Atlas formed somewhere else, around a different star, in a different part of the galaxy, possibly billions of years ago. It's been wandering through interstellar space ever since, and now it's passing through our solar system like a cosmic messenger. The nickel and cyanide we're detecting? That's a direct sample of chemistry from another stellar neighborhood. It's like receiving a package in the mail from another country. You can learn a lot about where it came from by analyzing what's inside. And what we're learning is that the universe is far more diverse than our solar system led us believe. The chemistry we see here in our little corner of space is just one example of how planetary systems can form. Out there, across the galaxy, there are star systems with different temperatures, different radiation environments, different chemical abundances. And the comets that form in those systems reflect those differences. This is why scientists are now using these chemical signatures to try to figure out where 3I/Atlas came from. Based on its trajectory, we know it's coming from the direction of the Milky Way's thick disk, a population of older stars that formed early in the galaxy's history. In the last 10 million years alone, 3I/Atlas has passed within about 3 light years of 25 known stars. But which one, if any, was its parent? That's still a mystery. What scientists can say is this: wherever 3I/Atlas formed, the conditions were different enough to produce a comet with a chemistry we've never seen before. And as we detect more interstellar visitors, thanks to telescopes like the Vera Rubin Observatory coming online soon, we'll start building a catalog of these chemical fingerprints. Maybe we'll even be able to trace them back to specific star systems. Imagine that. A comet arrives from deep space, and we can pinpoint exactly which star it came from, billions of years and trillions of miles away. That's the future we're building toward. Right now, as I'm recording this on October 16th, 2025, 3I/Atlas is behind the sun from Earth's perspective. We can't see it. Ground based telescopes are blind. It's a configuration called superior conjunction, when the sun is directly between us and the object we're trying to observe. But that won't last forever. Around late October, early November, 3I/Atlas will emerge from the solar glare, and telescopes will be able to observe it again. By then, it'll have passed perihelion, its closest approach to the sun, which occurs on October 29th through 31st. Perihelion is always the critical moment for comets. The intense solar radiation and gravitational forces can transform them, igniting outbursts, reshaping their tails, revealing hidden structure. Scientists will be eager to see how 3I/Atlas has changed. Did it fragment under the sun's heat? Did new gases activate? Is the nickel emission still there, or did something else happen? We'll find out soon. And when we do, it'll add another chapter to the story of this interstellar visitor. But even beyond that, there's a bigger picture here. 3I/Atlas is only the third interstellar object we've ever detected. Three objects. That's not enough to build solid models or draw broad conclusions. We need more data. But that's coming. The Vera Rubin Observatory, set to begin full operations soon, will scan the entire sky every few nights. It's expected to discover dozens, maybe hundreds of interstellar objects in the coming years. And each one will be a new chemical fingerprint, a new piece of the puzzle, a new window into how planetary systems form around other stars. The textbooks we're rewriting today, they'll need to be rewritten again tomorrow. And that's exactly how science is supposed to work. We observe, we test, we revise, we improve. Every anomaly, every unexpected result, every contradiction is an opportunity to learn something new. 3I/Atlas, with its nickel and cyanide, with its missing iron, with its unique spatial distribution, is teaching us that the universe is more creative, more diverse, more surprising than we gave it credit for. And the lesson is clear. We can't assume that what we see here in our solar system is the only way things can be. Out there, across the galaxy, there are star systems with different rules, different chemistry, different physics playing out on cosmic scales. And when those systems send visitors our way, when comets like 3I/Atlas cross our path, we have the privilege of studying them. We have the chance to expand our understanding. We have the opportunity to see the universe as it truly is, not just as we imagined it to be. So here's what we learned today. 3I/Atlas is releasing nickel and cyanide in patterns that don't match any solar system comet. Nickel is concentrated close to the nucleus. Cyanide spreads farther. Iron is mysteriously absent. These chemical signatures are forcing scientists to rethink fundamental assumptions about how comets form, what conditions exist in other star systems, and how we can use interstellar visitors to study the broader galaxy. For decades, we thought all comets were basically the same. Now we know better. The universe is far more creative than we gave it credit for. And 3i slash Atlas is the proof. Thanks for watching. If you enjoyed this deep dive into interstellar chemistry, hit that like button and subscribe for more content about the weird and wonderful universe we live in. Drop a comment and let me know. What do you think is causing the nickel emission? Metal carbonyls? PAHs? Something we haven't thought of yet? I want to hear your theories. Until next time, keep looking up. The universe has more surprises waiting.